From Photonics Media, this is All Things Photonics, a podcast shedding light on industry-shaping advancements in lasers, optics, imaging, metrology, and sensing. Each episode, our hosts speak with luminaries, rising stars, and market leaders about the trends shaping the current and future landscape of photonics. From space and deep-sea exploration to precision timekeeping and advanced manufacturing, this is the podcast for progress on All Things Photonics. This season of All Things Photonics is brought to you by Polyscience and Thor Labs.
Today's episode is brought to you by Polyscience. For over 60 years, the Polyscience line of award-winning temperature control equipment has been helping the photonics industry reach its goals safely and efficiently. Our products are made in America and delivered globally. Please visit polyscience.com to learn how we can help you. Changing the world of chillers is more than a tagline. It's a part of our history. Today's episode is also brought to you by Thor Labs. Thor Labs believes in the positive impact of photonics and hopes today's discussion inspires you. We're a vertically integrated photonics designer and manufacturer dedicated to making your ideas successful. To join our team or to learn more about our stocked offering or custom solutions, visit thorlabs.com.
Silicon photonics and photonic integrated circuits. Where else would we think to kick off Season 10 of the All Things Photonics podcast? This diverse technological landscape holds considerable promise to boost bandwidth and drive major reductions in power consumption. Key to fulfilling this promise, utilizing existing manufacturing infrastructure, scalability is essential for data applications amid the blossoming AI age. The subsets that comprise the semiconductor space have been significant investments through the CHIPS Act and its foreign equivalents, and for good reason. Power consumption and data consumption from data centers is quickly reaching unsustainable levels. Our first guest of the season is Anthony Yu, Vice President of GlobalFoundries Computer and Wired Infrastructure Business Unit, which manages the company's Photonics project. GlobalFoundries is the recipient of the first major funding packages awarded by the CHIPS Act and stands as the third largest semiconductor foundry by revenue behind TSMC and Samsung. In our conversation, Yu speaks to the potential of silicon photonics to meet the growing needs of data centers and AI, its challenges, and some of the areas GlobalFoundries is working to progress through its photonics program. In part 2 of our episode, we're joined by John Jost, co-founder of Enlightra, a Swiss startup developing chip-scale optical frequency combs. In a sit-down with news editor Joel Williams, Joe speaks to potential applications, the ins and outs of telecom, and some of Enlitra's recent progress. Season 10 of the All Things Photonics podcast with GlobalFoundries' Anthony Yu is up next.
So tell us about GlobalFoundries' approach to silicon photonics. How long have you guys been involved in this space, and what are some of the company's key innovations?
Joel, first of all, thanks for having me here on the podcast. I really do appreciate it. GlobalFoundries has been working on photonics for a while. We've been kind of working on it, starting with the pluggable transceivers based in our Singapore location, and we did some work there. But more notably, we're on our third generation of silicon photonics foundry technology here in Malta, targeting both pluggable transceivers, but also now for co-packaged optics, which is nicely timed given all the interest in generative AI. So we're one of the first people, in fact, I think we were the first people to offer a 300 millimeter silicon wafer with silicon photonics for a foundry offering.
Excellent. Can you tell me a little bit more about the co-packaged optics? I'm curious, kind of what the applications are with that technology.
Yeah, it's a often bandied about term, and sometimes it's not as precise as people would like it to be. But basically, what co-packaged optics addresses is a problem that they have relative to getting the computing power off of GPUs and CPUs and getting it off as opposed to using copper. Instead of using copper, we use light. So co-packaged optics is simply packaging the optical transceiver, which converts electrons to photons and then photons back to electrons in the same package as the typical single-digit nanometer ASIC, and allows it to be packaged on the same part at very short distances. And that allows you to get high bandwidth of data on and off the ASIC and transport it over long distances within the data center. So it's kind of a combination of photonics technology which is what we've really been focused on at GlobalFoundries, but combine that with packaging technology, which allows you to package it within the same form factor as the very high-end and very powerful computational ASIC.
Excellent. Now, what would you say are sort of the major frontiers in silicon photonics right now that your company is working on?
Well, frontiers is a broad term, so I'll take it in a direction that I think we can expand on. So I think what's been remarkable is just the rate of growth of bandwidth over the last few years. I'll tell you, when we first started, Joel, when we first started Silicon Photonics at GlobalFoundries, people were working with 40 gigabit and 100 gigabit pluggable transceivers. But literally driven by things like large language models, that rate of computation has probably increased twofold over 1 year. And now we're talking about 800 gig and 1.6 terabit type of bandwidths. But the biggest challenge we have in Foundry is keeping up with the rate of bandwidth, but also balancing bandwidth growth with energy efficiency and power consumption. As you know, there's a big problem today with these data centers driving enormous amounts of electricity. And so it's easy to drive lots of bandwidth, but you also have to, not really easy, but the trick is actually balancing that bandwidth growth with making it energy efficient so these data centers don't end up consuming vast amounts of and disproportionate amounts of electricity.
Sure. Now, as you've mentioned, silicon photonics has, so much potential for enabling things like data centers and AI while, reducing their power consumption. And we hear that all the time, so much so that it's almost lost its meaning in a way. So I was wondering, could you help put the technology's potential in that regard into perspective?
Sure. Well, I think silicon photonics, let's just look at those two words separately. So photonics itself has been around for a while in the form of 3-5 semiconductors. As you know, Joel, indium phosphide is a direct bandgap material. It lasers. And so there's been a long history of 3-5 semiconductors in the form of using very specialized and esoteric type of materials for that. Silicon photonics is the application of the high throughput, high volume CMOS manufacturing, based on 60 years of CMOS manufacturing and high volume, high yield economic models, but using silicon in a kind of an unnatural way to emulate the 3-5 materials and combine both active and passive materials onto one silicon wafer. So in my mind, silicon photonics is kind of emulating things that 3-5 materials, more exotic materials can do, but doing it at scale, Joel. Doing it at scale and using the vast infrastructure of tools and process control and yield learning and test engineering to allow you to bring photonics in a more mass way and bring those quantities of volumes and lowering the cost to allow silicon photonics to really make light much more viable for a variety of industries, not just data centers, but also medical devices, sensors, and even automotive.
Interesting. Could you expand a little bit on those applications that you mentioned?
Well, at GlobalFoundries, we're really focusing on the data center. So we're using silicon photonics, and we're doing it, as I mentioned before, for co-packaged optics and optical interconnects. We're doing it for pluggable transceivers. We're doing it for optical interposers, and we even have some customers using it for quantum computing and photonic computing. But we're seeing interest in photonics for things like medical devices. People are using medical devices, using photonics for medical devices, looking at changes in refractive index and allowing you to actually pair that with what virus may be detected for in-home virus type detection. We're seeing photonics enter the automotive industry. Think of a car as a data center on wheels. The amount of computing for self-driving cars is actually quite impressive. And some of these cars are going to have as many as 100 or 200 PICs, photonic integrated circuits, within each car. So I think as photonics becomes more of a standardized foundry type of product, you'll see that scale be brought to different industries.
Excellent. Now, what would you say is something that you yourself are particularly excited about as it relates to this technology, and why?
Well, every day I get up and I try to find ways to bring photonics to a reality. We have a very high-end CMOS fab here. That's where I am today in Malta, New York, where we do our most advanced processors. What we're trying to do, though, is we have a foundry corridor within this foundry. So we don't have a separate fab for photonics. So to me, the thing that I'm proudest of is a very controlled introduction of materials that are unique for photonics, Joel, within a CMOS fab itself. So we're able to look at introducing new materials potentially that will allow you to get from 200 gigabits per wavelength of light to 400 gigabits wavelength of light by introducing new materials. And you've read about these in the literature, things like barium titanate or lithium niobate. These are materials that are somewhat foreign to CMOS processing, but can be applied toward tooling and put into manufacturing flows, and then create that hybrid of manufacturing processing, where you can build photonic circuits within the environment of a CMOS fab. I think I'm proudest of that, for making something work in an infrastructure or bringing in new types of materials.
Awesome. Now, you mentioned those other materials. It was barium titanate, I think you said, and lithium niobate.
Yep. Those are the materials that people are looking at moving from the lab to the fab. Right.
Can you tell us a little bit about some of those challenges? As I understand it, certain materials can sometimes introduce difficulties when you're bringing them into kind of a manufacturing setting, particularly when you're trying to use some of the existing technologies. Could you expand on that a little bit and maybe tell us how GlobalFoundries is addressing those challenges?
Well, first of all, let me be very clear. We don't have those in manufacturing just yet. Those are ways off from getting into manufacturing, but we have a fair amount of foresight here at GlobalFoundries, so we're doing evaluative type work. There's a variety of materials, all that exhibit an effect called the Pockels effect, using physics, which allows you to get to the next level of electro-optical type of behavior. But these materials, as you note, Joel, some of them are pretty detrimental in terms of introducing impurities into the line. That would be both bad for photonics, but also really bad for CMOS as well. So I think we're looking at whether it makes sense for some of these materials, which are growing through things like molecular beam epitaxy. Should you be growing it within the fab, or should you be transferring it using things called 2.5D integration, heterogeneous integration? So without being too specific, you guys will find out when we do introduce these things into manufacturing a few years from now. We're looking at whether it makes more sense to be able to use a hybrid growth approach, or whether it makes more sense to package it, doing what we call die-on-wafer type integration. So those are the types of considerations that we have. Ultimately, what we want to do, though, Joel, within GlobalFoundries is find the most efficient, high-yielding, low-cost manufacturing method without jeopardizing the rest of the line for introducing these types of materials into the photonics foundry within a CMOS environment.
Excellent. And could you just talk a little bit about some of the capabilities that those materials introduce? You may have covered it already, but I think I might have just missed it.
Well, what they allow you to do is they allow you to, in simple terms, allow you to achieve better modulation. So they allow you to be able to increase the bandwidth of a device. Think of a modulator, for example, as the equivalent of a transistor. So it allows you to be able to process more data using photons at a much higher rate than what we're currently doing today using conventional modulators.
Today's episode is brought to you by Avantes. Unlock the power of light with Avantes. For over 30 years, we've delivered precision fiber optic spectroscopy, trusted for custom integration and reliable data. Discover how to empower your application, industrial, scientific, or beyond. Visit Avantes.com and experience spectroscopy solutions that innovate. Today's episode is also brought to you by LightPath Technologies. From concept through prototyping, volume production, and global distribution, LightPath has the optical knowledge and manufacturing expertise to be your optics partner every step of the way. Visit lightpath.com to learn more.
Here once again is news editor Joel Williams with co-founder and co-CEO of Enlightra, John Jost.
So now, before we get into some of the finer points of your company's technology platform, could you give sort of the bird's eye view of what Enlightra is and the space that it works in?
Yeah, sure. I'd be happy to tell you more about that. So at Enlightra, what we focus on is using developing multicolor lasers for a range of applications. But our primary focus is really on using them for optical communications. You're probably already familiar that lasers are used to send information, right? I assume that's the case, Joe, right?
Yep.
So what maybe most people is not familiar with is that anytime you want to send information, let's say longer than about 2 meters, you have to use lasers to do that. And typically what people do is you can send a single laser color down an optical fiber. You send information. It's called modulation, or it's not much different than just turning the laser on and off, like simply Morse code. However, right now there is a problem is we're reaching a limit to how fast or how much information we can send with a single color at a single time. And this problem is very similar to what happened with computer chips back in the early 2000s. If you remember back then, we used to buy our processors by the processor speed. It was, 1 gigahertz, and the next year it was 2 gigahertz, and so on. However, somewhere around like 2007, the advertising guys stopped using that as a metric to sell you new chips. It's kind of disappeared what the processor speed was. And the reason is they simply couldn't really go much faster. I think 20 years ago, you're at 2 gigahertz, and now if you kind of look down in the specs somewhere, you might be around 4 gigahertz processor speeds. But the way they were able to maintain this increased performance over time was not to have just one processor, but to have multiple processors. And it's very similar right now in optical communications. One color is not enough to send the information. You need to start using multiple colors. And this is where Enlightra comes in. And actually, this is really being driven in a completely new way right now by the AI boom. And the reason is with all these GPUs that they want to connect together to do all the large language model training, there's an insane amount of information that has to flow back and forth. So it needs to be a lot, it needs to be really fast, and these GPUs need to be well connected. And they're really hitting the capacity of what wires can do. So in the next generation, or maybe 2 generations after what we have today, there's a strong push to switch to using actually lasers and light, start connecting the GPUs together directly to be able to do all this large language model training. And that's really where Enlightra's multicolor lasers provide a big boost, and that's where we feel our biggest opportunity is moving forward.
Excellent. So now, from what I know about your company and some of the past coverage that we've done, Enlightra's key innovation, or at least one of the major ones, seems to be its comb laser, which I think you've mentioned.
Right.
Can you tell us a little bit about that and how it works?
Yeah, sure. I'd be happy to go into more detail about that. I'll try not to use too many technical terms.
Feel free.
Sure. Well, we'll see how far down the rabbit hole we go.
Sure.
I can put all your listeners to sleep if they really want to. This is at nighttime. No, so what Enlightra does is we can take a single laser, commercially available semiconductor laser that has a single color, and then turn it into multiple colors. Now the question is how do we do that magic? Well, it comes with using integrated photonics. So for the listeners out there, integrated photonics, it's very similar to, let's say, if you have a integrated circuit, like your computer chip, there's a little chip with many wires. Photonic integrated circuits are conceptually the same thing. Instead of electrical wires, it's say a light guide that you can guide the laser light in. And it turns out some of the materials that they use in these can have some special properties. And we make use of some of these special properties and also some unique designs and know-how that we have. Take a single laser and then we can actually split it up into many, many different colors. This could be 10, more than 100 colors. And they're very, very pure in color. They're very, very precisely spaced and well suited for all these optical communications applications.
Excellent. I was wondering if you could go a little bit into a little bit more detail about sort of the importance of color purity. I remember reading about one of Enlitra's collaborations, and one of the things that kind of struck me was what you guys talked about with color purity, and how a laser, typically it's not really as pure as you might think in terms of its color.
Yeah, no, that's true. And there's a broad range of, let's say, different types of lasers, and the color purity can vary dramatically between all these. And let's maybe go back and let's talk about something that people are usually familiar with, and that's, let's say, radio, right? So radio is an electromagnetic wave. You have your radio set at the 100 on the dial, an FM dial. That's a 100 megahertz signal, right? And when that's broadcast, it's broadcast with some purity. But if there's noise, let's say that frequency is jittering around, and that picks up as noise on your signal, and makes it then hard to listen to your radio station. It's very similar with some types of optical communication, particularly one that they call coherent communication. And coherent communication, it's in some ways similar to FM and AM radio combined. You use both the phase information as well as the amplitude of the wave to encode information. So now if that is shaking around in terms of the intensity or in terms of the frequency or the color, that leads to, let's say, degradation of your signal. And it turns out, let's say, the purer the color of your laser, or the purer the color of the wave that you're using, the more information you can encode on a given channel. So then the purer it is, the more information that you can send. So that's one of the really key things. And in our technology, the way we make our lasers, say, we can improve the color purity over a traditional, let's say, semiconductor laser by a factor of 1,000 or even 10,000, which is very key for doing this long distance communication. Now, this color purity is really important for really long distance communication, where they use both the frequency and the amplitude. Now, if you get down to the shorter distances inside the data center, they switch from something called coherent to, let's say, direct detect, where they're basically just looking at the amplitude change in the light. So this is very similar to, let's say, AM radio. In AM radio, you just change the amplitude of your wave. And in these very short regions, now the color purity becomes less of an important issue, but then more the amplitude stability becomes more of a dominant effect there. And Enlitra's technology, the way we produce these colors, it just inherently produces very, very pure, stable colors. That's one of the beauties of the comb lasers that we produce.
Excellent. Now, when we last covered Enlitra's comb laser technology, which I think was earlier this year, it was noted that it was operating in the C band, but that it works just as well in the major telecom bands. I was wondering if you could kind of expand on that and the reasoning behind that, but behind the choice of the C band. I understand there's a lot of different bands. So for those of us who aren't telecom people, what is the C band? What is it used for? And then practically speaking, where will this device be operating, when it comes to those band classifications?
Yeah, sure. So let me first say, I'm not a telecommunications guy either. I'm an atomic and quantum physicist by training, so I'm having to pick up all the telecom jargon as I go along. So forgive me if I make some mistakes here, the historical information. Now, as you mentioned, the C band, O band. So what do those actually mean? So there's also, not to be confused, there's also C bands and let's say the RF domain, but let's say down at much lower frequencies. But in the optical or infrared domain, there's the O band, which stands for the original band, and the C band, which has the very sort of exotic name standing for the conventional band. So the original band, O band, was the original set of colors they used. And the reason they did this was this was at 1,300 nanometers. And in here, fiber optics, it's relatively low absorption, but more importantly, it's one of the low spots for dispersion, which if you're sending a signal kind of tells you how much it's going to, let's say, shift in time, and that can lead to some errors. So in the early days, that was really important for them, having low dispersion. Now there's the C band, the conventional band, which is at 1550 nanometers. This is now one of the perhaps also very widely used. And the key thing about this wavelength range is this is where the glass and the fibers has the lowest absorption. And that's important if you want to send light over, let's say, long distances, like between continents or hundreds of kilometers. Then you have to use the C band. Whereas if you're sending things on the order of a kilometer or so, you don't care about loss. It's not really a significant issue. So in the telecommunications industry, there's really a sort of clear division. If you are inside a data center, everything is in the O band. If you're outside the data center, everything is done in the C band. And as I was discussing before, there's, let's say, coherent communication, and then there's this what we call direct detect, where you just do the amplitude modulation. Now, this is changing, but more or less today, there is also a similar barrier. Everything outside of the data center is more or less coherent communications, because that's really good for long distances. And inside, it's this direct detect. Although coherent, which is traditionally more expensive, a bit more complicated, it's slowly getting cheaper. And some of the advantages are pushing it, let's say, down to shorter distances. Now, coming back to Enlitra's technology, our platform, one of the great things about it is we're agnostic to the band. So the optical technologies that we use, we can make them work in either the C band or the O band. And, what's also important is, people talk, let's say down the line, you can actually fill up the capacity of the C band, and then people go to what happens if you go to other wavelengths. So there's a whole bunch of other bands. There's the L band for the long band, S for the short band. And these are other colors that are around that range. Our technology also can be applied there, but just at the market, there's not really much commercial traction for using those. But again, we're well positioned as the market starts getting more and more information hungry and wants to use the full capacity of every available fiber optic cable.
Now this. One of the things that really stuck out to me, covering your technology advance earlier this year, was the amount of possibilities that this really seemed to open up. Could you kind of expand upon those possibilities? And of course, feel free to include applications that are, might be a little bit far from technological readiness, as well as ones that you guys, really intend to kind of seize upon.
Sure. Yeah, no, I mean, we have a new type of laser technology, right? And as we know, lasers were invented back in, the late 50s. No one even envisioned all the different crazy things that they would be doing. I mean, Charles Mann, I'm sure, never thought that people would be using it for hair removal when they invented the first laser, right. Ruby laser, right? And all the other things. So yeah, anyways, lasers, forgive the puns since I'm here in Switzerland, but our comb lasers are really like a Swiss Army knife. They can be utilized for a lot of things. And actually, we, as a startup company, we started out saying, our technology is great for all these different things, but then we realized we need to focus in order to develop the company. So that's why we chose, again, this path of optical communications and really, again, focusing on connecting GPUs together. However, that being said, yeah, you're right. There's many other specific applications for comb that have really exciting possibilities. And probably interesting for the listeners to hear about a few. So some of the classic ones for, let's say, comb lasers, and in other jargon, comb lasers are called optical frequency combs. It's another way of saying the same thing. But the concept of optical frequency combs is actually what the 2005 Nobel Prize in Physics was awarded for. And that original application related heavily to timekeeping. So if you want to do next generation clocks, such as atomic clocks or optical atomic clocks, the comb lasers or the optical frequency combs serve as a sort of gear mechanism that allow you to link the RF domain to the optical domain where you have your reference. And so that's one of the original applications for comb lasers, is telling time. That also has applications to, let's say, GPS or GNSS. So if you want to have really accurate positioning, you need really accurate clocks. So all the clocks in satellites right now are atomic clocks. And in the future, those next generation atomic clocks will hopefully be based on lasers and light transitions of atoms. So also related to that is something called spectroscopy. So that's if you, let's say, have a gas or a molecule and you want to figure out what it is. One way to do that is to pass light through it and see what colors it absorbs. And if you want to do that very precisely, then you need very precise colors to do that. And that's exactly what a cone laser provides. For example, I think people are pursuing this for, let's say, example, even glucose sensing. So it even applies to things that are much closer to home and personal applications. Another really cool one that I have a friend that's been working on it at DESI to be his hair. And this is using combs to search for planets. One of the ways they look for new planets is you take the sunlight, and then if a planet is going around the sun, it causes the sun to wobble, which causes a Doppler shift on the light coming from that. And then if you look at the spectrometer, you can see subtle periodic changes in the light. Now, the question is how you measure that. So you basically, what you need is a ruler for light. So you have the light, and how do you tell if it's changing? You need something that's always stable right there, so you can say, that color is moving a little bit. So cone lasers can provide that reference. Now, moving closer to, let's say, real-world applications that affect people is there's some cool new things coming with fiber sensing, where, under all of our cities, there's these immense fiber optic networks for telecommunications. And we're only using them to send data. There's several companies actually pursuing, let's use this giant network to sense what's going on. And fibers are really, really sensitive. They can potentially sense, let's say, traffic patterns. Where's there a lot of cars moving? They're already used to sense changes in buildings or bridges. So now you have this massive fiber network. And so cone lasers are also well suited to be able to do all this detailed probing. And another application, again, relates to autonomous vehicles, or what's called LiDAR, using light to sense moving objects. That's, again, something that's really, really in vogue. There's many different ways to do that with lasers. You don't necessarily need a cone laser to do that. However, in some applications, cone lasers can do some really cool things. Actually, I think several years ago, my co-founder, Maxime Karpov, had a paper in Nature where they used a cone laser to do a super cool LiDAR experiment. So what they did is they had their laser beam and they shot a little pellet bullet across the laser beam. So this pellet was moving around 130 meters per second through the beam. And why it was transversing the laser beam, they used the cone light to measure the surface roughness. So they could measure the surface roughness down to 200 nanometers. And so that's roughly, a thousandth of the diameter of your hair. They could sense that while the beam was going through. So it's very well suited for some of these type of LiDAR applications, especially like for industrial distance measurements. So I'd say, those are some of the applications, that I find personally the most cool, but there's many other ones as well. Actually, let me highlight another one.
Sure.
I should highlight it because we have a project on it. And this is next generation computing. So right now there's the big trend is, let's say, GPUs to, let's say, do all this AI training. But essentially what AI training models are, it's if you've ever had linear algebra and you've multiplied vectors and matrices, that's really all you're doing. And it's computationally difficult. However, it turns out you can do this very efficiently also in optics. And one of the ways you can do that is you have a particular, let's say, special way to write the matrix on some light-sensitive array of interferometers. And then you can use multiple colors to interrogate that and do very, very high-density, high-capacity processing. And so that's one. It's much farther term. There's a few companies working on that, but it's something for the future to also help enable this AI boom when it's needed.
Excellent. Now, I wanted to just quickly circle back to some of the applications that you mentioned. We'll take like optical clocks, for example. Mm-hmm. Now you mentioned that comb lasers have applications in that, and optical clocks are, of course, incredibly accurate. Does the increased color purity provided by Enlitra's comb lasers, does that translate to like greater accuracy with the optical clocks and maybe, for example, greater sensitivity with the like the fiber sensing networks that you've mentioned?
Mm-hmm. So let me separate out those two different applications. So let me first go back to optical clocks. I think in reality, so the way an optical clock works is it's just your gear mechanism. So the clock is only as good as the reference. And the way it happens is you have your very pure reference laser probing some atoms, then you reference that to your comb. So basically you transfer that purity of that very, very pure laser. So this is something that's crazy pure, a whole different level, and then that gets transferred onto your comb. So you're not really then relying on the inherent stability so much of the comb. That being said, I think there are probably other types of comb, optical frequency combs that are well suited for clocks. I mean, ours can work as a way to miniaturize it down, but I think if you really wanted the best of the best stability, there's perhaps some better ways to do that. Now, coming back to the fiber sensing, this is very different, right? So here you need a sensitivity that is good enough to be able to sense what you detect. You need something that's small and compact, and that's affordable, right? For the optical atomic clocks, you need spend $100,000 or $200,000 on a comb, and that's fine. But for fiber sensing networks, that's not. Right. So this is where our Enlightra's technology fits very well, and we're just starting an EU project in that direction as well. And again, here, our performance is more than good enough for this fiber sensing as well as the stability. We can put things in a tiny, tiny package as well as scale the costs for, let's say, to meet the price points needed by such a market.
Excellent. That's really interesting. The sort of the differences between there, where the comb laser is might not be quite suited for producing the most accurate optical clock, but it's very well suited for miniaturizing it. Whereas with the fiber sensing networks, it's really seems to be, by the sounds of it, kind of a perfect fit for that application.
No, we think
it's really interesting.
Yeah.
Awesome. Now, I wanted to ask, how are things progressing at Enlightra? You guys are a startup. Is there anything you guys can share regarding, any research collaborations or projects? And how are you guys progressing towards commercialization?
Yeah, no, things are going, crazy fast, it feels like for us. 2 years ago, we were 3 people, office with no lab. Now we're 21 people with a lab, and now this very vertically integrated. So now we have some initial, systems, prototype systems that out with customers for being tested and feedback. So it's been a really exciting development to actually have something in the hands of the customer. And, it's a big step once you do that, right? Because it's out in the wild and you don't control it anymore. So things are going really well there. Where we're going right now is in really focusing from selling, let's say, turnkey devices, which we have now, to scale things down for this optical application of connecting GPUs, which is called optical interconnect. But again, we have a range of collaborations. For example, we're collaborating with IBM on this photonic computing applications. Infinera is a part of our collaboration for doing fiber sensing, as well as working on next generation manufacturing techniques for photonic integrated circuits with the EU project with Acceloprint, and working with people, other telecom experts in Dublin to help test our devices. So, it's really, as a startup company, you don't have all the expertise. So partnerships are a key way in order to be able to expand and grow what you're doing.
With that, we conclude another episode of All Things Photonics. Thank you to our sponsors, to the technical staff behind the scenes, and to continued support from the Photonics Media editorial team. As always, questions, comments, thoughts, and ideas are welcome. Let us know how we're doing via email at allthings@photonics.com. All Things Photonics is available on all major platforms and on our website, photonics.com.